Yeah, we can start. So good morning, everyone. Now it's a Thursday of the APCTP Winter School. The first speaker is Raghu Mahajan from Stanford University. He will teach the recent progress in information loss paradox. Yeah, please welcome him.
Okay, thanks, Yangi. It's a real pleasure to give these series of lectures, and I've been great to visit Korea for me for the first time, but I guess it's not possible in the time of the pandemic, and I hope everyone is doing well and healthy and safe. Please ask questions whenever you think something is unclear or deserves more clarification. It's fun to make it just participatory, more things. Okay, so I'm going to talk about some recent progress in the black hole information paradox. And it is great that the Donghan's lectures are also part of this school. And hopefully the stuff I cover, I think it's complementary. So we will, hopefully you can learn from both lectures, different material. Anyhow, so I just want to start by introducing the key players. So we know that black holes form from the collapse of a star, right? So if just some star undergoes gravitational collapse and there's nothing to stop it, eventually it becomes black hole. And the classical GR says that nothing can escape the interior. Even light cannot escape. And one way to draw this is in the Penrose diagram. So we have the singularity, the scri plus and the scri minus. So here I'm drawing the Penrose diagram of a star, which is formed from collapse. So this dotted line represents surface of the star. This is the interior of the star. And the horizon would be, for example, here. And the point is that if we have any light ray that's in this region, even though whether it's ingoing or outgoing, it ends up at the singularity. So nothing can escape. Okay, so that's one feature of the black hole, that nothing escapes the interior. The other feature is the singularity. And singularity simply means that the gravitational forces are infinite at the singularity. Now, of course, we believe that classical GR is a classical theory. So some quantum mechanics has to come in and affect, some quantum effects have to come in near the singularity and prevent its formation. Maybe, in a region of the Planck size near the singularity, quantum effects kick in. So we can ask, are quantum effects relevant for outside observers? If we have a person who never falls into the black hole, hopefully someone like us, they just stay here very far near infinity, is classical GR just enough? And quantum effects are very small and things like that. Okay, and you might think that the horizon of sort of, if we have a solar mass black hole, then the Schwarzschild radius is like 3 kilometers. It's pretty big. Or if we have a black hole of the mass of the Earth, the Schwarzschild radius is still macroscopic, is about 9 millimeters. So, and then you might think, okay, at the horizon, there is nothing special going on. We understand everything. Infalling observer just goes through, et cetera, et cetera. But then Hawking in 1974 showed that actually quantum effects are relevant even for outside observers. That there is some particles that appear to be emitted from the horizon. And horizon is a place where we think we understand the physics. So Hawking's derivation is undoubtedly correct. Like we can't say, oh, there is something unknown about quantum gravity and we don't know what's going on. Okay. So Hawking says that some particles appear to be emitted and they carry energy. But Hawking also says that these particles, he derives the fact that these particles are completely in a mixed state, are in the thermal density matrix. So the quantum state of these particles that's being emitted is a density matrix. It's not a wave function. It's not a wave vector. And so it's a mixed state. Okay, that's fine. But now imagine the back reaction. So as the particles are being emitted, particles carry away energy. And so the black hole horizon gradually shrinks. And it shrinks and shrinks and shrinks and completely disappears. Okay, and eventually disappears at a very, very long time scale. But it does disappear. So what we have achieved is that the initial star, right, whatever it could have been, is just converted by the end of this process into some thermal gas, completely thermal gas. So this could have been in some pure state. This could have been a wave vector, and this evolution sort of evolves us into some kind of a density matrix, some kind of a e to the minus beta h. And the information problem is that this is inconsistent with unitary evolution. Because evolution in quantum mechanics happens via e to the minus IHT, where H is a Hermitian Hamiltonian. This is a Hermitian operator. This is a unitary operator. And in particular, it takes pure states to pure states. We can't have this. So this is inconsistent with unitary evolution. So something has to be, there's something missing. And this is this famous information loss paradox. So this is just introduction. Hopefully everyone has seen some version of this story, but I just want to pause here to just ask if there are any questions about this. Okay, seems like everyone is on board. Okay, now we can ask some more detailed question. One diagnostic, whenever we have some quantum state, rho, like, okay, let's say we have some quantum state psi, and this system psi has like is divided into two parts, A and B. So for us, A could be the black hole, the remaining black hole at some stage of the evaporation, and B could be the Hawking radiation. Okay. So the idea is that there is some spatial slice. So this, I'm drawing some spatial slice through our universe. There is maybe some black hole horizon here. This is R sub S. It has been emitting particles. So there is some cloud of Hawking radiation far away. And we imagine sort of making a bipartition somewhere here. So whatever is inside the orange, we call it the black hole. Whatever is outside the orange, we call it the radiation, the Hawking radiation region. Okay. And of course, it's only the joint state which is pure. And let's say we are the faraway observer, we live out here, and we care about the state of the radiation. So the state of the radiation would be some mixed state. It would be the trace over the black hole degrees of freedom of psi, right? And this will, in general, be some mixed state, and that's fine. Now, a very important quantity for mixed states is just S of rho rad. It's the von Neumann entropy, is defined as minus trace rho radiation log of rho radiation. It's a trace rho log rho. Rho is a positive definite Hermitian matrix with trace 1. So this log is well defined, and this number is some positive number. Okay, so the question that the fact that rho radiation appears to be a thermal density matrix, just means that it has some non-zero entropy. Well, it doesn't mean just that. It means it's mixed state, but one of the things a mixed state means is that its entropy is non-zero. Okay, so Don Page asked the question in 1990, early 1990s, what does the entropy of Hawking radiation look like as a function of time? So we have time here. Let's say the black hole was formed at time t equal to 0, and it starts to evaporate by Hawking radiation. And let's say this is the complete time of evaporation, T evap. Okay, and so what is the expectation here? And here we want to plot S of rho radiation as a function of time. It's just a number, it's some real number. So it starts at 0 because initially we just have no radiation. And then one particle comes out. This one particle is in a mixed state, so it has some entropy. Like let's say it's some qubit in some bell pair with its some entangled with some degree of freedom in the black hole. So the entropy goes up by 1 unit as time goes on. And another time unit passes by, you emit another particle, entropy starts to go up. And Hawking in 1974 would say that the entropy just keeps going up until the black hole has evaporated completely. So we start with S initial equals 0 from some pure state, and we end up with S out equals a huge number. And this is, again, inconsistent with unitarity. A unitary evolution preserves the entropy of a state. Okay, but Don Page said, look, guys, there is A system and the B system. And what is happening is that the amount of radiation as a function of time is increasing. So essentially, sorry, I drew this wrong. A is the black hole, B is the radiation. Originally, A is most of the system, and we have radiation here. Slowly, B is becoming larger and larger, right? Okay, so since B is becoming larger, we have the entropy going up. That makes sense. But beyond the halfway point, let's say black hole has half evaporated, and let's say we are at the 70% evaporation point or something like that. Then B forms 70% of the system, right? That's the Hawking radiation, and A is just 30%. Now, S of B, you might think, okay, it's just some 70%, you have some number here, and that's the answer. But there's a very important property of von Neumann entropies that if AB is in a pure state, then S of B is equal to S of A. And if the state of A is almost, again, some random state, almost like completely entangled, then we would only expect a 30%. We would expect entanglement only at the level of 30%, not at the level of 70%. So what this means is that after the halfway point, you should actually look at the entropy of the black hole, like how much black hole is remaining. And then you see this curve has to come down after the halfway point. So this is Page's prediction. Page says after the halfway point, you have too much radiation, there is too little of the black hole remaining, and there is not enough room to satisfy this equation, S of B equals S of A. So this tent-shaped curve in what I highlight here in yellow is famously called the Page curve. And this up here is Hawking. And I really want to emphasize the stark nature of this. This has nothing to do with really quantum effects near the singularity and so on and so forth. At this point, a black hole is only 70% evaporated. That means 30% of it is left. 30% of a big black hole is still a huge black hole. The radius of the Schwarzschild radius might not be 3 kilometers, might be 1 kilometer, but it's still pretty big. And here we have a deviation, which is maybe like, an order 1%, like 60% mismatch been in the Hawking's prediction and Don Page's prediction. So this is huge. Like, okay, this is not have something to do with real tiny effects coming in near the singularity or anything. It's a big mismatch. And the puzzle since Page's work was how to account for this difference. Like, what is it that's going on? And the recent progress that was made starting from papers in May of 2019 was to explain this curve, like how this Hawking curve bends downwards and agrees with the Page curve. Okay, so that is my introduction. And again, I want to stop here for questions. Okay, and
sorry, but
yes.
Hawking's original argument assumes black hole remains the same.
No. Hawking's original argument was based on some semi-classical computations. So his computation says that whenever a black hole emits a particle, that particle has some fixed amount of entropy. It's always in some thermal state. So he had not taken into account this equation, this SB equals SA.
I see.
And Page's curve, right? It's not a derivation. So I want to emphasize this. So Page's 1991 paper is a general expectation for quantum systems. For any quantum system, it could be a hot gas, it could be, the standard model, it could be anything. Not gravitational, for any quantum system, gravitational or not. And it was argued based on, we have some random vector in the Hilbert space. The Hilbert space is like a sphere, like the set of unit vectors in Hilbert space. And you just partition the system into M and N, and M qubits and N qubits. And you just find the entropy of a random state in Hilbert space as a function. So it's a purely just a mathematical computation. The puzzle is to explain how GR plus quantum mechanics agrees with the Page curve. This is the puzzle. Because Hawking just followed his nose. Hawking computes in this theory and finds that the general expectation is violated. So how do we explain that? Yeah, thanks for the question. Is that clear?
Yeah, thank you.
Okay. Okay. And Donghan's lecture go into much more detail about the original derivation of Hawking, but I just want to sketch one very picturesque view of how it comes about. So how this entropy is created and so on. So I will not now draw the Penrose diagram, but this Eddington-Finkelstein diagram. So we have some star collapses. By the way, a really beautiful illustration of this is in the Nobel Prize website. So Roger Penrose got the Nobel Prize this year, and the website has a really good drawing of a collapsing black hole and the light cones and so on in this Eddington-Finkelstein coordinates. So this is the star. It collapses. There is a singularity. This is R equals 0. As usual, this is roughly time. And we have a black hole horizon forming here. So this is the horizon. And here is the horizon. Okay. So we have our observer here outside, right? He lives here. And we want to draw, usually to define a state in a quantum field theory in space-time, or in any system in space-time, we need to pick a Cauchy slice. We need to pick a codimension 1 slice. in space-time on which we define the Hamiltonian, we define the quantum state. So out here, there is no problem. We just pick some Cauchy slice. Okay. Now, you see, because of the singularity at late times, the Cauchy slice can't just go through like that, like horizontally, right? Because there's a singularity there. So what the Cauchy slice has to do is, okay, it can enter the horizon here, but then it has to bend. It has to bend like that. And then it can come up and go out like that. And this slice that I drew on the Penrose diagram would not look as weird. It would just look some slice like that. Here is the horizon. So this point here is the point where the Cauchy slice meets the horizon, like point P. We may call this P prime. Here is P prime. And the region between P and P prime on the Cauchy slice is in the interior. But you see, it has to avoid the singularity in this way and go in. So as you keep moving the time further and further, these Cauchy slices have to keep avoiding the singularity, and you have to draw them like that. So what happens is there is no time-like killing vector on the Schwarzschild geometry. The killing vector which we have outside becomes space-like on the inside. So the point is that moving along these Cauchy slices from one Cauchy slice to the next, moving from one Cauchy slice to the next is not a symmetry. So the quantum fields that live on this on the spatial slice see some time-dependent background. They see the time-dependent background is like saying the Hamiltonian is time-dependent, right? Because there's a gravitational system, there's a black hole. So the quantum fields, you would have something like d4x, root g, g mu nu, d mu phi, d nu phi. So scalar fields know about the metric, and the metric is that of a black hole, maybe an slowly evaporating black hole. But nevertheless, the point is the background geometry presents a time-dependent Hamiltonian. There's no way to make it static. And we know from time-dependent perturbation theory that if you start out a quantum system in the ground state and you apply a drive, you apply a time-dependent Hamiltonian, the system does not remain in its ground state. They're just transitions. Like the Fermi's golden rule gives you probabilities that what is the probability that a system will be in some excited state at some later time. And excitations of quantum fields are basically particles. So we start out the quantum field in its vacuum where there are no particles. And then you form a black hole, there's a horizon, there's this time dependence coming from the stretching of these slices as they try to bend and go around the singularity. And all that does is it starts to excite the quantum field. So it creates like particle pairs. So you get these things. And in each unit of time, you get more and more particles. So each unit of time you go in, you have more stretching. And so by these wiggles, I represented some excitation of the field. This would be like a particle. So this would be like particle 1 and particle 1's partner. So the particle 1 at the next instant of time moves further along, and a new particle is created, like 2 and 2 prime, and so on. So the stretching goes on. And now you see Hawking's result that if you only look at the particles outside, like 1 and 2, so 1 and 1 prime are in an EPR state, are in the Bell state almost. 2 and 2 prime are in a Bell state. So if you only capture 1 and 2, their entropy is like 2 times log 2. So, and then at each instant of time, you get like 1 unit of entropy more. And essentially, there is nothing to stop this. In Hawking's rate picture, horizon is big, it's smooth, and this stuff just goes on forever. And you get you get this curve of Hawking, that the one that keeps going up and up and up. Okay, so this is like sort of Hawking radiation in pictures, and this kind of cartoon of these wave packets is due to a review paper by Samir Mathur. He explained this very nicely in one review that he had. Okay, are there any questions about this? Okay, so with that is my motivation, and hopefully we will get to the evaporating case towards the end of these lectures. But for now, we are going to transition to some simpler examples. And there's going to be a little bit of a disconnect between what I have motivated and maybe the next hour or two. Oh, sorry, there is something in the chat. Oh, I can send the reference later. Okay, I'll send it to Zhangyi and he can circulate it. Okay. All right. Right. So there's going to be a bit of a disconnect for the next maybe a lecture or lecture and a half, but you will see how it connects. The goal, which we will do in all detail, all the calculation, I will present all the calculations, is to have a version of the page curve in which doesn't look like the one before, in which the naive curve is like this. This is the naive curve. And the page curve should look something like this. Okay, so the only difference is that instead of going to 0, it just has to become flat after some time. And this will have all the conceptual ingredients that go into making the tent as well. But since the tent computations are calculation technically more involved, I will not present them in detail, but refer you to the original papers. But this curve between the naive prediction and the page prediction, this one, we will derive in all detail. Okay. And okay, so let's just get into it. We have been discussing entropies, right? Von Neumann entropies. And entropies in a theory of gravity. Our best understood examples of gravity theories, quantum theories of gravity, are the ones in ADS. So we have this ADS CFT duality. Let's say for now, since I'm going to do some concrete example, let's say we are in ADS 3 CFT2. So we have a 1 + 1 dimensional CFT, which lives on the boundary of 3-dimensional ADS. Okay, so I will draw a few pictures. So this here, circle, is the spatial manifold of the CFT2. And there is time. Okay, and then if we put in the time, there is the cylinder. So we have R times S1. R is time, S1 is space. And in ADS3, we take the cylinder and fill in the bulk. So it now becomes R time times a disk. And the disk has a boundary S1. So we have here this, and there's a disk. And so that's ADS3. And so this is ADS3 space, and it has some action, like there is some gravitational action, D3x, root G, R+6, and stuff like that. It doesn't matter. It's just some anti-de Sitter space, uniformly negatively curved Lorentzian space. Okay, so now we have this duality. This is just some CFT, some quantum system with no gravity, which we understand. And we can make some partition, right? So we can divide up the system into A and B. A is this interval, and B is the rest of the interval. And let's say we are in the ground state of the CFT, ground state. So that's the global state. So we have some state 0 AB. And we want to ask compute rho A. Well, we don't want to compute the density matrix of A. We want to compute the entropy of the density matrix restricted to the region A. So we have the global ground state, we have a subregion, and we just want to ask what is S of rho A. And the answer is really beautiful, conjectured by Ryu and Takeyanagi and later proven. So now, since we are just in a time-independent situation, I'm going to forget about time. So forget time for now. Okay, so here we have the spatial circle S1, which is the boundary of a disk. And we have here our system, this region A. What Ryu and Takeyanagi said is that here's how you should compute the entropy of rho sub A, of S of A. Okay. First, you have to minimize something. But what do you have to minimize? You have to put some surface here in the bulk, like some random surface. Let's call it like little a. Little a is some surface whose endpoints agree with capital A. And it just has to be such that its area is minimal. So amongst all candidate surfaces which have its boundary, anchored to A, we have to find the minimal one. And that's it, that's the answer. And once you have that minimal surface, the area of the surface gives you the entropy. Okay, so now we are just going to do actual computation and derive what the entropy of a CFD2 looks like. And we will use this later on as well, just to serves to illustrate the point. So this was in global ADS. To make life simpler, we will work in Poincare ADS3, Poincare patch of ADS3. In which, so the spatial geometry is the hyperbolic space, H2, but in the upper half plane model. So we have upper half plane. And the boundary of H2 is R, right? It's just the real line. So now our CFT lives not on S1, but on R. So it's just some infinite manifold. Instead of living on a compact space, it's living on R, just because the formula is simpler. So we have here R, and we have here our interval A. Let me put the origin of coordinates here. Call this direction Z. So this is the Z direction. This is Z equals 0. And we know the metric. So let me call this direction X. Let's say this is negative L over 2. This is L over 2. So our interval has length L. And we want to find the minimal area surface that ends on these 2 points. Okay, at this point, we know, or we can derive as a homework exercise, that geodesics minimal length curves in hyperbolic 2 space are semicircles. So here we have a semicircle. And amongst all curves ending on these points, the semicircle has the minimal length. Okay, and we want to now compute the length of the semicircle. So, okay, that's fine, we can do that. So what's the equation of the semicircle is Z squared plus X squared equals L squared over 4. But we have to remember that this is hyperbolic space and not flat space. So the line element is dz squared plus dx squared over z squared. This is for hyperbolic 2 space. Remember that the full metric, we are in ADS3, there's also a dt squared component. But since we are just working on the t equal to 0 slice, we can forget about the dt squared and just focus on the. Okay, so now since in the numerator we have z and x, it's useful to introduce polar coordinates. So we put here the origin, we introduce like a radial coordinate and the angle theta. So what this becomes is dr squared plus r squared d theta squared, right? That's the numerator. And the denominator is z, and that's r sine theta squared. So z would be r sine theta, and x is r cosine theta. Okay, and we just want to compute the length of a constant r slice, constant r, because the geodesic is a semicircle, right? Because it's a semicircle. So the length we want, length of geodesic, is the integral from 0 to pi. Okay, we have a semicircle, starts at 0, goes all the way to pi of r d, well, the r cancels, sorry. So we just get d theta over sine theta, right? This would be because we drop the dr and r squared cancel, we have just d theta over sine theta from 0 to pi. Notice that this is just twice from 0 to pi over 2 d theta over sine theta. And this factor of 2 will play a crucial role in some of the computations we do later. The point is simply that we had the semicircle here, and theta equals 0 and theta equals pi are near the boundary of ADS, right? This is the boundary of ADS. And distances are big in the boundary of ADS. So this integral has a divergence, at theta equals 0 and theta equals pi, which is at the ADS boundary. And this we expect. We expect these lengths to be infinite because we're in hyperbolic space. And this represents the fact that also the entanglement entropies in a continuous quantum field theory are infinite. They're infinite because of UV divergences, like between modes here and modes here. So there's some entanglement, and there's a divergent amount of entanglement. Okay, anyway, so so you might say, okay, how do we compute this? This is just infinite. The point is we are supposed to put some cutoff. We are supposed to put cutoffs in ADS CFT at z equals some epsilon. So we have to pick this surface here at z equals epsilon and cut off the integral there, right? Which means that the theta integral will also be cut off at some small near theta equals 0. So the minimum value of theta is going to be this, right? This point, a cutoff point C. And essentially our length is going to become 2 times integral pi over 2, the upper limit, and the lower limit would be 2 epsilon over L, d theta over sine theta. Why is this 2 epsilon over L? Because remember, z was r sine theta and r was L over 2, right? We are on a geodesic of radius L over 2, and theta is approximately theta when theta is small. And this is epsilon here. So the cutoff value of theta is 2 epsilon over L, which is what I wrote here. And now we can just do this integral. You can just do it as elementary, and you get 2 times logarithm of cotangent epsilon over L. I mean, the cotangent is not meaningful because we took small epsilon. So this is really 2 times log of L over epsilon, right? Because at small argument, the cotangent behaves like 1 over x. So we get 2 times log of L over epsilon. And okay, so the entropy of an interval of length L was 1 over 4g times this length. And so that is like 2 log L over epsilon times C over 6. What is C? From the Brown-Henault analysis, Brown-Henault told us an entry in the dictionary between ADS3 CFT2 that the Newton's constant in ADS3, G or G Newton, equals 3 over 2 times C. where C is the central charge. C measures if your conformal field theory is a bunch of free bosons, C counts the number of bosons. So it's like a measure of the number of degrees of freedom. So if we plug here G equals 3 over 2C, we get the C over 6 times 2 log L over epsilon. And this is precisely derivable from purely CFT2 techniques. This was done by Cardi and Calabrese. So this answer here matches. So we did a computation of just some length. It was some geometric object, and somehow it computes for us this highly complicated thing, like it's a density matrix of infinite dimensional quantum system. And okay, so that's the expression. Okay, are there any questions about this derivation? Or this C over 6 will come again and again in our anyway. Okay, so I just want to generalize this quickly. So we got a result which is C over 6 times 2 log L. Let me delete the epsilon. It's always there. This is the answer for the entropy. This is also equal to, of course, C over 6 log of L square. Okay, but what was L, right? L we had, now I'm drawing here time and space, and we just had some interval of length L. But in a general situation, the interval A may not lie on a horizontal slice. The interval A could be tilted. As long as it's space-like, this is allowed, right? So the endpoints of the interval A, which I'm calling P and Q, may not lie in equal times. So how are we supposed to compute the entropy in that case? The point is we can write this C over 6 log L square, but the generalization is easy. It's L square minus T square, where T is the time separation here. So if this is T, the time interval between P and Q, and X, so this is just the Lorentz invariant generalization of the previous object. Okay, so I'm going to write this as delta X square minus delta T square, where delta X represents the separation, the X separation between the endpoints, and delta T represents the time separation between the endpoints. And introducing light cone coordinates, which we will use also many times, we have delta X plus, delta X minus, with an overall minus sign. So just definitions, X plus will always be T plus X, and X minus will always be T minus X. Okay. And essentially, I just want to write the answer for the interval PQ just one final time, log of delta X plus log of delta X minus. Okay, and this minus sign just goes to whichever one of these is negative. One of them has to be negative. We can put absolute value signs here if we want. Okay, so you see there is sort of independent contributions from the right movers, so to speak, and the left movers. So we know in a general CFT2, very generally, things factorize holomorphically. Things factorize into right movers and left movers, and we just see some independent contributions from them here. Okay, and one last thing that I will say is, what if we had a boundary? What if the CFT had a boundary? So that means that the CFT2 now lives on R time. Time is still R, but the space is R bigger than or equal to 0. It has a boundary. It's just a positive real axis. And okay, so here is our time, and here is space. There is a hard wall here. And usually we have to supply some boundary conditions. Like if you have a right left moving particle that hits the wall, what happens to it? And usually we pick reflecting boundary condition, that the particle just bounces right back. And after the bounce, it becomes a right moving particle. So it was a left moving particle. After the bounce, it becomes a right moving particle. What this means is that the left and right movers are no longer independent. I'm just motivating this result, but you can prove this along the lines of before. In that case, if we have an interval O P, let's say we have time, again, we have a boundary, and we have space, S of OP will just be one of these contributions. It will not have two. It will just be C/6 times 1 times log L, not 2. Like, because the right mover and left mover got identified, so we can just delete this one of these terms. So it's an important difference. Before we had this 2 here. And the 2 basically corresponded to the fact that we have independent contributions from the left mover and the right mover. When we introduce a boundary, that factor of 2 basically goes away. Okay. Are there any questions about this? Okay. Okay, let's move along then. And one final modification to the formulas. Because we have gravity, right? So far, I just discussed CFD2s in flat space. But now we are going to have CFD2 on a curved space, not in flat space, not on Minkowski space. Good thing is that any two-dimensional metric can be written as the flat metric. So I'm writing now in Lorentzian signature in the light cone coordinates times a Weil factor, which I will take here to be omega to the -2. So omega is called the Weil factor, and it depends on the position of where you are on the space-time. And essentially that's it. So the only information in the metric is in the omega. And now you see that the omega will come into the answers for the entanglement entropy. So we will have S, P, Q. Again, P and Q will represent some points in space-time. We will have C/6 log of delta x plus C/6 log of delta x minus, but we will have minus C/6 log omega at P minus C/6 log of omega at the point Q. So why is there this omega? It's because the UV cutoff needs to be implemented properly. So we need proper length cutoff epsilon. Proper length cutoff to be epsilon. So from the equation star, from the metric, we see that means that epsilon squared has to be coordinate cutoff square, coordinate cutoff squared times omega to the -2. And it's the epsilon that we have to keep fixed. So what that means is that the coordinate cutoff has to scale with omega. And so previously we had log of L over the UV cutoff. So now since the UV cutoff is proportional to omega, you get this log of omega of P factor here. So essentially, let me just write that out more explicitly. We have C/6 times, let me put it here, 2 log L. And the point is here, we have to put the proper cutoff. So that translates to omega times something fixed. So then you get, so you see how the minus log omega arrived in the previous equation. A more technical explanation than that, which is maybe the better explanation, is if you go to the Cardy-Calabrese derivation of the entanglement entropy, this entanglement entropy is computed by a 2-point function of some operators. And since they're just scaling operators, when we have a while factor, the correlation function depends on this omega at the points where the operators are inserted. So that is another way of seeing why the omega has to come into this formula. So this will be sort of our master formula in navigating our way through entropies and black holes and curved space and so on. So this is really the key player. Okay. All right. Fine. Okay, but again, there is a lot of background material in this initial lecture that we have to get through. So I apologize that we're probably not going to be able to get to something interesting today. But let me just do one thing and then we'll take like maybe a 2-minute break. So root Hakenagi needs to be upgraded. So in order to make this progress on the black hole information paradox, it's not enough to just have root Hakenagi and compute some areas in a gravitational system. We need to upgrade it. And what do we need to do to upgrade? So here's our system again. Here's ADS3. I'm drawing ADS3 here. There is some spatial slice. And there is some interval here, A, whose entropy we want to compute. We again pick some bulk region, the shaded region here. And first we define a so-called generalized entropy functional, which depends on this region. I'm going to call the region R. Okay, R is the region, Sgen of R. Maybe make this a little bigger. So we have this region R here. And the definition of this, it's a definition, so I put this colon here. It's the area of this wiggly surface as before, so area of del R over 4G. By partial R, I just mean this wiggly thing, the thing I called little a before. Plus the entropy of the matter fields in R itself, so in the shaded region. Point is in ADS3, we don't just have geometry. We have some graviton, maybe we have some scalar fields, we have some gauge fields that are all moving around in the bulk. And those particles are themselves have some entanglement across the surface, across this little a surface. So you have to, this is the upgrade. This term is the upgrade from root Hakenagi. So this is explained in a paper by Engelhardt and Wall. And why they consider this combination, area over 4G plus the entropy of the matter in the shaded region, is because it goes back to the work of Beckenstein, where he showed that when an evaporating black hole, the area is decreasing. So you might think that the entropy is decreasing, and that contradicts the second law of thermodynamics. But he showed that if you add the entropy of the matter, then it's still good. Like the second law is satisfied. So this is the motivation to consider this combination. But then the result of Engelhardt and Wall says that S of A equals min, again, just Sgen of R. So instead of minimizing just the area, we are minimizing a new combination. So earlier we just took a geodesic, right? Now it's not enough to simply take the geodesic. You first have to compute this complicated object, area plus S matter, and then extremize that. And then this Sgen functional evaluated on that minimal surface equals the entropy of the region A. That's the new proposal. That's this proposal by Engelhardt and Wall, and we believe it's a correct proposal. And such a surface is called a quantum extremal surface. what precisely this little A surface is called the quantum extremal surface. Okay, so we will use this abbreviation QES quite a bit in this lectures. Okay, is the definition clear of the quantum extremal surface and how it's an upgrade from Ruta-Kenagi? Okay, all right. So I suggest maybe since we've been going on for 55 minutes, we take maybe a 3 minute break. And if people want to ask questions and in the chat or just speak, we can do that. I'll be here, but feel free to step away, have some water or something. And all right, so next, like three-dimensional gravity is very hard to calculate. You see, this area this formula is an upgrade, but it's also almost a useless formula. Why it's useless? It's useless because computing these entanglement entropies is almost impossible if you're in 3 dimensions or higher. So if you're in ADS3 and you ask me compute the entropy of this 2-dimensional region with a funny shape, form an arbitrary shape, you're just not going to be able to do it, even for a free scalar field. It's just not known, and we don't know how to compute it. So you might say, okay, just go home. You can't do anything. This is good, but RT was at least useful. I could compute some length, and I could compute the entropy. So what do? We have to take a downgrade. We have to take a downgrade from ADS3 to ADS2. Okay, so that this area over 4G plus S matter, so that this S matter now is the matter living in a 2-dimensional space. This is the matter living in ADS2.
Can I ask a question?
Yes, please.
So the matter, can you define the matter precisely?
I will do that very precisely in I'm going to do that in maybe 10 minutes.
Okay, thanks.
Yeah, exactly. Yeah. Okay, so this is the thing we need to do. But see, now we are confused. What is area? Area here, notice that in ADS3, we were taking length. So it's codimension 2 area. It's codimension 2. But codimension 2 in ADS2 is just a point. So what do we mean by area of a point? It doesn't mean anything. It's 0. So that's why we need to work with these so-called dilaton theories of gravity. Which is not just a metric, but it's a metric plus a scalar field, phi. I'll call it phi. And what? So I'll write down the action, and then I'll say what the area means. So as most of you probably have heard, that there is this really simple theory of gravity called JT gravity, whose Euclidean action as a functional of g, mu, nu, and phi is the following. There is a constant phi naught times integral of d2x root gr plus integral of dx root gamma times 2k. G is the metric, and I'm just using gamma for the metric induced on the boundary. Okay, notice that in 2D, the Einstein's equations are an identity. They're just true for any manifold. And this thing is the Euler character of the surface on which you're trying to define your theory. So this is some boring term. It doesn't give any equations of motion. So we have to add something here. We have to add integral d2x root g phi times r plus 2. That's another term. Sorry, I left out the 16 pi g here. So there's a 16 pi g, which I just put on the left-hand side. And we need some term here, dx root gamma 2 phi k minus 1. Okay. So the first term is topological, but the second term is interesting. Now we have phi and r plus 2. So you see why what will be replaced by the area. So the area over 4g gets replaced by phi over 4g. Because if you think of this phi as the length of a third dimension of a circle, so we could have gotten this theory of ADS2 by dimensionally reducing from ADS3. And this phi is sitting next to the root g. So it's like the length of the circle in the higher dimension that we reduced on. So, and that would have been the area in the 3D theory. So that's why this area gets replaced by phi over 4g. And since codimension 2 is just a point, it's like phi at the point P. A candidate quantum extremal surface is just a point or a bunch of points. And we're just supposed to take the value of the dilaton at the point over 4g as our area. Okay, so this is the theory we are going to consider. And since someone asked what is matter, matter means the following. So our theory would be IJT of g mu nu and phi plus I action of some chi and g mu nu. So chi is just some scalar field. And it couples to the metric. And this is maybe some free scalar field action or free fermion, whatever you want. But I will take it to be a CFT with central charge C. So this is a matter. This is the definition of the theory. This we call the gravity sector, and this we call the matter sector. Does that answer the question? Yeah. Okay. We won't need to be very specific about what the action is, but we just need to know that it's some two-dimensional CFT, okay, that's coupled to the metric, and then the metric is coupled to this dilaton. The role of the dilaton is to define what we mean by area in a 2D theory of gravity, etc. Okay. All right, but now we need to construct some interesting solutions in this theory. We have this theory of gravity. It doesn't look like our 4D theory of gravity. So what do we mean by a black hole? Like, what is it that will evaporate? Whose entropy will be compute, et cetera, et cetera. So the first comment is that ADS2 should be dual to a CFT1, right? Just by holography. This is just some quantum mechanics system. It's just some time. And if you want, at the back of your mind, you can imagine the SYK model. So the SYK model is like some n fermions. Well, think of it as a quantum dot, like you have engineered something, it's very small with just like n particles, and it moves in time. And the dual description is a two-dimensional anti-de Sitter space. So this will be the boundary theory. Okay, that's comment number one. Comment number two is okay. Now we have to get down to the to like actually working with this JT gravity theory. So okay. So let's get. So I'm going to write the action again. Phi times r plus 2. The boundary terms don't contribute to the equations of motion, so we will focus on this piece of the action. So when we do delta delta phi, right? Of course, we get r plus 2 equals 0. So what this says is that the Ricci scalar is constant negative -2. And since the Ricci scalar is sort of the only degree of freedom in the metric, this says that the manifold, space-time manifold, is locally hyperbolic space, or ADS2. Strictly hyperbolic 2 space. What do I mean by locally? Like the global structure could be different. You could have the upper half plane modded out by some discrete group, subgroup of SL2R or something like that. Or you could just have the hyperbolic disk with some other kind of boundary. Point is, it's locally in every neighborhood, it's a hyperbolic space, but the global structure might be different. There might be some boundaries, or there might be some global quotients that make the space compact. But that's what the R plus 2 equals 0 means. But now we also have to take delta delta G mu nu. And that sounds a bit hard because you have G here, R here. And just for pedagogical reasons, I'm going to do this in a bit more detail because I think people write it down, but sometimes don't explain how this equation comes. The basic relations are you can find in a GR book, the delta R. So we make a variation, and I will make a variation not of the metric, but of the inverse metric. It's just easier to write the formula. It's delta GAB. So this is the first term. But we have two total derivative terms, grad A, grad B, delta GAB, plus grad C, GAB, delta GAB. And okay, that's the variation. We can derive this, but we can also look it up in vol or something like that. And there's also a delta of the square root of G, the metric, which is this one is more familiar, G half, GAB, delta GAB. Okay, so when we make the variation in the action, you see that these total derivatives will get thrown onto phi, because we will have delta of G to the 1/2 times phi of R plus 2. This doesn't do anything because R plus 2 is 0 from the other equation. So we can drop that. But we have G to the 1/2 phi times this whole thing here. Sorry. Like just this thing here. And now when we do the integration by parts, you see that these total derivatives. Sorry.
무서워. 나 이거 조절을 잘 못하겠어.
그럼 이거를 이렇게 오늘 해두시고 여기.
Okay. Yeah, so I think maybe this is fine, and then we have to throw these derivatives on phi. So the equation that we get, grad C phi from this term minus times GAB, that's here, minus grad A grad B phi minus phi times GAB equals 0. And here I have replaced RAB by 1/2 R GAB. Since R is -2, this equals negative GAB. So RAB, so let me just number the terms. This is number 1, this is number 1 here, number 2, it's number 2 here, it's number 3, it's number 3 here. So this is some second order equation for phi. So it's just grad square phi GAB minus grad A grad B phi minus phi times GAB. Okay, and we can try to solve it. But let me give you a very simple solution to this equation. And the other equation was R plus 2 equals 0. So this we can solve by taking ds squared equals minus dt square plus dz square over z square. So this will solve equation, sorry, let me call this equation 2, equation 1. This solves 2. Okay, how about 1? If you analyze 1, and you can do this as a homework exercise, the most constraining equation is the zz component of the equation. So when you put A equals B equals Z, the trace part is trivial, and the time part follows from the ZZ part by taking a derivative. So the ZZ component is the only equation where I'm assuming that phi only depends on Z. So I want to look for a static solution where there is no time dependence and so on. So if you assume that phi is only a function of Z, then you only need to compute the ZZ component of this equation. and it reduces to z phi prime plus phi equals 0. It's actually a first order equation. The second order pieces cancel. Okay, so we have this, and then the solution is simple. Phi is just some constant over z. So this is our solution.
So you consider the stationary solution for just motivation, but later you then you consider like a evaporating black, or in general you consider
exactly.
some.
Yeah, as I said, I won't be able to cover the details of the evaporating case because the equation is very messy, but indeed. So in the May paper of 2019 by Almeri, Engelhardt, Marolf, and Maxfield, those people did actually solve this equation as a function of time. And there are some general formulas you can write down, and they're there in the paper.
Okay,
But yeah, you don't also, this 0 will get replaced by T mu nu. Once you have it being sourced by some matter field, the TAB will go here. If you normal Einstein's equations are GAB equals TAB. So the TAB actually goes here. But right now we are just looking at a simple vacuum solution. Or even when we have the matter, its stress tensor will be 0 because we'll put it in the 0 temperature state. Anyway, so this is the solution. But I have been a bit quick in that I have done the solution, but I haven't told you what the boundary conditions are. A theory is not just defined by the action, but you also need boundary conditions. So JT gravity boundary conditions are that that ds square should approach near the boundary minus dt square over epsilon square. Epsilon is some UV cutoff. This is saying that the metric is big. So the component of the metric is epsilon to the -2. Epsilon is a small length scale. It has dimensions of length. So this just says that the metric should become big near the boundary, constant metric. But also we have the other field phi. And the boundary condition is that phi should be equal to phi r over epsilon on the boundary. Okay, so phi r is a dimensionful parameter of the theory. It's part of the definition of the theory. Parameter, and it has units of length. And this will be a key player again, like it's this thing that sets the length scales. Notice that something has to set the length scale because G Newton in 2 dimensions is dimensionless. So we don't get a Planck length from G. So this phi r is the object that basically up to a big change, but this is the thing that sort of morally plays the role of a length scale in the gravitational sector of the theory. Okay, so what this phi r does, it basically means in this solution we should take phi equals phi r over z and put the boundary at z equals epsilon. So then we will satisfy all boundary conditions. Even the metric at z equals epsilon would be satisfied by dt square over epsilon square. Sorry, give me 1 second, yeah. Okay, sorry. Okay, so we have our solution. We satisfy the equations of motion, and we also satisfy the boundary conditions. Okay. Are there any questions about this solution? I'm going to draw the Penrose diagram. We have here time. And I'm going to put z in this way. So the z in ADS, there will be the origin of z here. So this will be z equals 0. And so the ADS2 would be just defined by Z negative, just for convenience. And the Poincare patch that we have drawn here looks like this. So this patch is what we have described by this above thing. And lines of constant Z are like this. So these are lines of constant Z. And then we have a cutoff surface just here. This would be like Z, the red line is like Z equals minus epsilon. I put minus just because I put positive direction that way. So the red line is the cutoff surface. Okay. Okay, no questions? Okay, let's go and then compute our first quantum extremal surface. Okay, we are computing a quantum extremal surface, but whose entropy we are computing? The boundary is a CFT1, right? One is just time, so its spatial manifold is just a point. And we can't further subdivide a point. A point is just a point. So all we can compute is S of the full boundary. And since there is no subdivision and we have put everything in its ground state, right? So it's a pure state, so this should be 0. It had better be answer 0. Moreover, I should have said this, I completely missed it. So here, back to the quantum extremal surface, imagine you have done the extremization and you have found a nice, smooth quantum extremal surface here. So this is the QES. There is a refinement of the QES statement is that it not just computes entropy, but the region A, let me add a page here. The region between little a, the QES, and capital A is the so-called entanglement wedge of big A. And the point is that ADS-CFT has substructure. It's not just that the full boundary is dual to the full bulk, but that subregions of the boundary are dual to subregions of the bulk. So again, I draw this many, many times, but we have capital A, we have found our QES, little a. This shaded region is encoded. By encoded, I mean any operation that you might want to do completely localized in the shaded region in the bulk. You can do that on the boundary in the region capital A without requiring access to the complement of A. So you see that's the substructure of ADS-CFT. So this QES is it does two things. One, it's SGen evaluated on the surface tells you what entropy it has. And then the region between the QES and the boundary region tells you how much of the bulk you have access to if you only had access to the boundary capital A and you didn't have access to the complement of A. Okay, so this is important But coming back sort of here, since we have the full boundary, full ADS2 should be dual to the full boundary. So what this means is that our QES should be all the way to the Poincare horizon. And what this means now, I'm just drawing the ADS2 figure here. We have here our point is where the boundary lives. This is the entire spatial slice. Candidate QES, could have been here or here or here. And then this is the region that would be dual. But since the full boundary is dual to the full bulk, it had better be that the entanglement wedge is OH. Entanglement wedge had better be the full Cauchy slice.
Here, boundary is just a point.
It's just a point, exactly. It's just a point, and we can't make any further subdivision of a point. So that's why the entanglement wedge of the boundary should be the entire ADS2. So this means that
you also consider t equals 0
slice.
Yeah,
but the states are defined at a time slice. So the any state of a quantum system, we have to go to some Cauchy slice and even on the boundary, right? So the time, just some time evolution of the state.
Okay.
So QES must be at H. So this we can just deduce from general common sense. Like if this whole business is supposed to make any sense, this had better be the case, that the QES lies at the horizon, right? Now, how do we show this? What do we do? Okay, we have to go now to this SGen. Okay, so let's draw our ADS. We have our slice here, 0. And here, let me put a candidate point P with coordinate -a. Its coordinate is negative, so a is positive. So P is a candidate QES. Okay. What is this SGen? SGen as a function of A. So definition was area over 4G plus S matter of OP, right? Okay, what's area? Area we concluded was phi at the point P, right? Area is not area, but it really means phi of P. And I'm going to set 4G equals 1 because G is dimensionless, so I can do that. So phi P plus S matter of OP. What is phi of P? It was on the solution. Remember, phi of Z was phi R over negative Z. Dilaton is positive, so I have to put minus sign here because Z is negative overall. So it's phi R over A, with this phi of P, plus, okay, now what do we write for S matter? Let's remember our master formula from before. We had a C over 6 log of delta X plus a C over 6 log of delta X minus C over 6 log of omega at point P minus C over 6 log of omega now at the point 0, right? Okay, but this point 0 is not, we are going to do a derivative with respect to A, right? So this does not depend on A. The only thing that depends on A is this P. So this piece we can just drop. It doesn't matter for the extremization. If we have a boundary here, it's like a boundary CFT. The matter part of our system lives on a boundary CFT. That means if we have this chi quanta coming in here, it bounces back, right? ADS. So we will only get one of these contributions, as I emphasized before. The left and right movers are not independent, so we only get one contribution. So this is actually just not there. Okay, so let's write the remaining two terms. So we have C/6 log of, what's delta x plus? The point O has coordinates 0, 0. The point P has coordinates 0, -A. I'm writing P and then Z. Right? So delta x plus is just A here. Or in x plus x minus coordinates, because we would just have here A, right? What's omega? Remember, the metric was ds squared was minus dt square plus dz square, omega to the -2. This was the definition. And we have the metric of ADS2, which is dt squared plus dz squared, z to the -2. So omega is equal to z. So we have minus C/6 log of A again, because omega equals A, right? So this and this cancels. And essentially we just get S gen of A equals phi r over A. It's very simple now to extremize this and say minimization happens at A equals infinity. And that is the point H. So QES is at H. So just to draw this again, we have our ADS2, we have the point O, and we just found the QES all the way here. And this ES is the entanglement wedge. So this is just a sanity check. There is nothing very surprising here. Okay, in the last 1 minute, I will compute a second QES, but we will get into the meaning of that more next time. So this will be our first example of an island. You might have heard this term, non-trivial QES called an island. This is going to be very fast, but we will come back to it in the beginning of the next lecture. So just to give you a taste. So now we have ADS2 here. We have this system with the boundary. We have our SYK dot, the dual description, just some moving in time. Okay. What we do is we attach a wire here. So this is some real wire with some spins or some electrons coming in and interacting with these fermions. So if you were a condensed matter theorist in a lab, you would have the SYK Hamiltonian, you would have the Hamiltonian of the wire plus some coupling. Okay, so this is now our new system. We have attached something to it. And okay, and we let the system reach its combined ground state on this side. What this means on the picture on the left is that this wire is just a non-gravitational system in flat space. So you have to attach a half space here. So this side is ADS, and this side is flat space, completely flat. There's no omega, there is no JT gravity, no anything, just matter. So now what happens? The only difference that happens is this chi field is coming in like this. It doesn't bounce back, it just goes like that. And similarly from here, like any quanta that you might have sent in from the left can just go here. So now we have these fully transparent boundary conditions, and now we have a CFT living on the full space, not on a space with a boundary, but just on some Minkowski space. So now you can again ask, I have my SYK coupled to the wire. What is the entanglement of this part? Just the SYK. If I trace out the wire, what is the entropy? And what is the quantum extremal surface? What is the region in the bulk which is dual to this dot? So we will again compute S gen of A. it will be equal to phi r over a plus c over 6 log a. But now there will be a factor of 2 because there's a left mover and a right mover, minus c over 6 log a from the omega. So now you see these two terms don't cancel. You get phi r over a plus c over 6 log a. So this now is some simple function, but it's a non-trivial function. We have to extremize this. We take a derivative, phi r over a square plus c over 6a. And this implies that there's an a star QES at phi r times 6 over c. Phi r, remember, was a length scale, so this makes sense. And the only thing to notice right now is notice that this is not infinite. It's less than infinity. So what this means is that now with this situation of this Poincare patch coupled to flat space, our new QES is here, somewhere here, at a finite location inside ADS2. And this is the entanglement wedge. So if I call the quantum extremal surface Q and O, we learned that the SYK part of SYK plus wire is dual not to full ADS2, but only to OQ. Okay, and next time I will put the name that this region here between the horizon and Q will be the island surface, will be the island region. But we will get to the meaning of that and so on next time. Okay, thanks a lot.
Thank you for a great lecture and the clear explanation. Feel free to ask any questions.
So maybe I can send the reference of the Mathur paper and find it.
Okay, I will upload in the website or
Okay.
send the email,
Yeah.
either way.
Oh. Okay. I should say that, yeah.
Would you explain once again why the wrapping factor omega appears in the entanglement entropy?
Why the Weil factor appeared in the entanglement entropy?
Yeah.
Okay. So let me give both arguments again. One is the argument from twist operators. So if you read the Cardy-Calabrese derivation of the entanglement entropy, we have here our time and space. And let's say we are trying to compute the entanglement entropy of this interval. How it's computed is that you actually insert some operators here. They're called twist operators. So let me call it tau and tau. And the entanglement entropy, S of the interval, is given by the correlator of these fields, tau, let's say at 0.1 and tau at 0.2. These twist operators have some dimension. Okay, so typically in flat space, we would write its correlation function as 1 over x1 minus x2 raised to 2 delta phi, right? But if we are not in flat space, the correlation function is different. It's equal to omega of x1 to the delta phi, omega of x2 to the delta phi. And then you have to take some limit of n goes to 1 and take some derivatives. But the point is, this is how the omega enters. It enters just in the correlation function of the Cardy-Calabrese twist operators. That's one explanation. The second explanation, which is maybe more physical, is that we have ds squared equals negative dx plus dx minus times omega to the negative 2. And essentially, what happens is that instead of having c over 3 log L, over epsilon, this gets replaced by C over 3 log L over omega times epsilon. Why? Because let's take omega to this side, right? Omega squared ds squared. This epsilon is the physical proper cutoff, proper. So omega times epsilon proper is the coordinate cutoff. So that's why it appears like this, because when you do a Weyl transformation to get rid of omega, you compute the correlation function of the twist operator now in flat space, but you have to remember that your UV cutoffs are now different. It's essentially the same, but in terms of lengths, it's maybe easier to visualize that.
I see. Thank you.
Okay.
Can I ask a stupid question?
Yes.
So you showed the page curve and Hawking's results.
Yeah.
Yeah, and how is it related to the Beckenstein-Hawking entropy of black holes?
Good question. How is the page curve related to Beckenstein-Hawking? So I drew here, time, and I was drawing here S of rho of the radiation, right? So there had a Hawking curve, which was naively just increasing. But there is something else which is decreasing, which is that the area is continuously decreasing. Area of black hole is decreasing, right? Just because it is shrinking. It's emitting energy, it's shrinking. And Beckenstein-Hawking entropy is basically equal to the area, right, over 4G. So it's also decreasing.
Yes.
So it starts large, but it's decreasing like this. It goes to 0 when the black hole has completely evaporated. So essentially, this downward part of the page curve is the Beckenstein-Hawking entropy of the black hole, right? So this is S Beck-Hawk as the black hole is evaporating. And this makes sense because after the halfway point, I was drawing these systems A and B. After the halfway point is system A, which was the black hole, is the smaller system. So its entropy, its Beckenstein-Hawking entropy should also be equal to the entropy of the radiation. Right? So this downward curve is actually just a plot of the area of the black hole. And it's decreasing, and then the actual entropy increases, and then just switches to this at some point. So that's how the Beckenstein-Hawking enters the page curve. Here we are assuming, sort of implicit is the assumption that Beckenstein-Hawking entropy, which is basically the area of the black hole, is the number of sort of qubits that make up the black hole. So we imagine here that if when viewed from the outside, like I was drawing this picture, here we have the black hole, and we sort of surround it with some surface to divide the radiation from the black hole. We sort of assume that essentially we can replace the stuff inside the orange circle by area's worth of number of qubits, right? So that's why it cannot be more entangled more than that. Like if I have 10 qubits here and 100 qubits here, my maximum amount of entanglement can only be 10. It cannot be 100. Right? So this 10 is the thing that is being determined by the area, or the area of the black hole, or the Beckenstein-Hawking entropy.
Okay, I see.
Yeah.
Thank you.
Yeah, it's really.
Question? Yeah, so go ahead. Yeah.
Yeah, I just want to emphasize again that really the Hawking radiation is coming from the stretching of these slices near the horizon. And the reason we want our Cauchy slice to go smoothly to the horizon is because we believe there is just some space there. Like we don't believe that the space ends at the horizon. We believe it continues through. And therefore, when we draw this Eddington-Finkelstein diagram with the horizon like this and so on, right? We want the Cauchy slice to go through the horizon smoothly and then join on to some segment like that. And the arguments of so why Hawking radiation is there is because of this. Because if you didn't have to enter the interior region, you would have just a time-like killing vector, because outside the horizon, you have a time-like killing vector. So the fact that you're forced to enter the horizon in a smooth way, where you lose the isometries of time translation, that leads to sort of this particle production near the horizon. So there is an implicit sort of assumption of smoothness of the horizon. So it's like a tension between that the smoothness dictates that you produce these particles. And then in the end, unitarity says that, oh, something should have been wrong about that process. That's like the real tension of the information problem. Okay.
So it sounds like a masters this phosphor does not have then what happened with that phosphor?
Yeah. So I don't know much about fuzzball, but it's this argument is in some review where later he then says that fuzzballs is the answer and so on. But I think the weakness of the fuzzball proposal is precisely what you're pointing out, is that if you do replace it by a fuzzball, then you don't have the argument for Hawking radiation anymore.
Oh,
because you see, Hawking radiation relied on the existence of a horizon, which is empty, more or less. So, now if you say there's a fuzzball all the way out to the horizon, then just everything is off. Like the first assumption of Hawking about these Cauchy slices going through the horizon goes away. And so it's a challenge for the fuzzball to accommodate this. But I think that's maybe too far-fetched to ask, because till now, only they compute zero temperature extremal black holes in fuzzballs. But I don't know much about the literature. That's my outsider's view. Some of the challenges.
Okay, thank you. Any other question? I have one. Yeah, go ahead. Yeah, so one guy's.
Yeah, I have one question.
Yes.
Yeah, so actually, I didn't understand why did you introduce the example of SYK plus the wire example. So I didn't catch the point.
Yeah. It's a great question.
Yeah.
So why we introduce this wire? Why do we need to do this? The point is, a black hole in ADS is nice that we have ADS and we have ADS CFT and blah blah, but black holes in ADS don't evaporate. They are stable, they just stay there, they emit some Hawking radiation and come into thermal equilibrium with their radiation.
Mm-hmm.
So if we want to mimic flat space black hole evaporation, we need to do something. So imagine you are in ADS5 black hole. It's dual to some n equals 4 super Yang-Mills theory, right? It's just some e to the minus beta h of the super Yang-Mills state. There's a thermal state here. Now imagine the way you make this black hole evaporate is to make this n equals 4 super Yang-Mills talk to some heat bath, right? If I literally have a system of quarks and gluons and whatever, and then I put it in a heat bath, and let the heat bath suck the energy out of the n equals 4 super Yang-Mills, this will cool down, right? It's hot, but as the heat bath takes away its energy, if the heat bath is colder than the n equals 4 super Yang-Mills, the super Yang-Mills will cool down. And what that means is that the black hole in ADS will start to shrink. So the purpose of the wire is to make the black hole evaporate so that it just doesn't stay there forever and stuff like that. Because we want to mimic the flat space black holes with ADS. So this wire allows us to do that. It allows us to use ADS for the SYK or the n equals 4 but then allows us to carry away its energy further away.
Okay, thank you.
But yeah, I introduced here some zero temperature system, but next time, or maybe in the third lecture, we will get to the finite temperature story, where we will see the page curve like this.
So I have a question that here you show this Poincare patch and there is Poincare horizon. Usually, I mean, is there any like a possibility that the entanglement wedge can go beyond this Poincare horizon, or?
Yeah, so you see here when I meant the Poincare horizon, I should maybe I was just using misleading terminology. What we really have is that the entire Cauchy slice is dual to the SYK. That's the statement.
Nice.
And you see on the Cauchy slice, there is nowhere more to go. Like this is not some finite place, right? This is infinitely distant. This is far away, infinite in this direction. So that's the statement, that the full SYK is dual to the full ADS2 at zero temperature. Now, one comment I should make here is that when we draw this Poincare patch, you know, what goes on in this region? What's happening here? Like, why don't we just consider global ADS2? The point is there is a dilaton, right? We have a dilaton field and it's phi over z. A dilaton goes to minus infinity here. Okay. So here the dilaton is going to plus infinity, and then as you cross this horizon, it goes to minus infinity. So this is actually where the singularity is of the black hole. So the reason you're supposed to terminate here is because there is this cutoff curve, and beyond it is the singularity. So this is a time-like singularity because for people who know about more about ADS-JT gravity, it's the dimensional reduction of charged black holes in higher dimensions. So this singularity of the dilaton going to minus infinity is the time-like singularity of Reisner-Nordstrom black holes in higher dimensions. And this is the patch sort of we focus on. And similarly, there is singularity here. And when we go to finite temperature, we will see that the singularities will move. It will no longer be there. It will come maybe a little downwards. Like when we have the finite temperature, when we draw it like this, the singularity is actually here now. It's just wherever the patch ends, like that's dictated by the dilaton profile. Similarly, like here.
Yeah, okay, thank you.
Okay.
Is there
Can I ask one question?
Yeah.
I'm actually just trying to think.
Okay.
But it's an easy question. What should I think about the relevance of the partition function of the gravity theory in this situation?
The partition function of the gravity theory, yeah. So it's the usual thing. So if you do Euclidean ADS2, and let's say you compute it for the hyperbolic disk for H2, you compute Z of JT gravity. This like, you know, like the Gibbons-Hawking computation encodes some thermodynamics of the space. So it will tell you, for example, the entropy as a function of temperature and so on and so forth. Yeah, the ground state energy and so on. So it's basically, if beta is the length of the thermocircle, this is like 1 over beta to the 3/2 exponential of some of this phi r that I wrote over beta, something like that. And from this you can derive, for example, the entropy, the Beckenstein-Hawking entropy at temperature T is like this phi naught that I wrote before, plus this phi r over beta, something like that, times 2 pi. So the partition functions encode this kind of stuff. And partition function on some more complicated hyperbolic manifold, like something with a genus or something, contributes some non-perturbative corrections to this stuff.
I see, but obviously this has to be consistent with what we discussed today, right?
Yeah, and it is actually. So I didn't discuss the finite temperature case today, but we will see that this value here is precisely the saturation value of this kind of a page curve. So the thermodynamics comes in because it tells you, where the page curve had to saturate in this example that I will discuss next time.
I see. Thank you.
Yeah.
Any other question? If not, let's thanks the speaker again.
Okay. Thanks a lot.